right now, as you're sitting down or maybe you're out for a walk, your brain is performing this incredibly complex, like high-speed mathematical calculation.
Oh, absolutely. Constantly.
Yeah, and you don't even think about it. But if we peel back the skull and look at the hidden mechanics of balance, we find these tiny microscopic rocks and fluid-filled gyroscopes.
Yeah.
And they are just working constantly, quietly, to keep you anchored to the earth.
Right. And to fully appreciate what the human body is doing right this second, we really have to recognize a massive paradigm shift in how science understands equilibrium.
Okay, a paradigm shift. How so?
Well, for centuries, researchers viewed balance as this purely passive mechanical property. I mean, the prevailing model was essentially a plumb bob, right?
Like a heavy metal weight hanging on a string.
Exactly, something that just settles under the force of gravity. The assumption was that if you tip over, gravity pulls on your body's sensors, and then your muscles react after the fact.
So under that old model, the body is basically like a heavy rock sitting at the bottom of a bowl. It naturally wants to rest at the lowest point, and it only really does any work when something pushes it up the side of the bowl.
Yeah, but the problem is that modern sensorimotor research completely dismantled that idea. Balance is fundamentally not passive at all.
It's active.
Highly active. It's a highly predictive computation. I mean, your nervous system never waits for you to lose your footing.
Oh, wow. So it's anticipating it.
Exactly. It's continuously generating these rapid-fire internal predictions about where your body should be in three-dimensional space, like in the next fraction of a second. And it aggressively cross-references those predictions against the incoming reality from your sensory organs.
Okay, let's unpack this. Because if it's not a rock in a bowl, it sounds much more like a drone trying to hover in a gusty wind.
That's a great way to put it.
Because a drone isn't just passively floating, right?
Right.
It's constantly firing tiny thrusters, it's calculating wind speed, making continuous micro-adjustments just to stay in one single place.
The concept of a highly active state of hovering captures the physiology perfectly. And when the internal prediction of that biological drone doesn't match the sensory reality...
Like a glitch?
Yeah, say your eyes report movement, but your inner ear feels completely stationary. That computational mismatch is what actually triggers the agonizing sensation of dizziness or disequilibrium.
So you aren't experiencing a broken physical part?
No, you're experiencing a software error in your brain's predictive model.
That is wild.
Yeah.
But to understand how that software error happens, we obviously have to look at the hardware, right? The internal sensors of this biological drone.
Right, the inner ear.
And discovering what those sensors actually were required some deeply bizarre historical experiments from what we found in the sources.
Oh, very bizarre. We have to look back to a French physiologist in the 1820s, Marie-Jean-Pierre Florence.
Okay, the 1820s.
Yeah, and up until his work, everyone since antiquity just assumed the intricate labyrinth of the inner ear was exclusively dedicated to hearing.
Just for sound.
Right. Anatomy focused entirely on the cochlea, which is that snail shell-shaped organ that processes sound. But Florence, he began performing highly specific lesion experiments on pigeons.
On pigeons?
Yeah, he was surgically severing the individual semicircular canals inside their inner ears.
I'm just trying to picture this.
Ah.
He's going in and cutting tiny loops of bone inside a bird's skull, not even knowing what they do. What did he actually see happen?
He observed something that completely shifted anatomical science. When he severed one specific canal, the pigeon didn't just stumble, it would start to tumble or spin violently.
Oh, man.
But specifically in the exact geometric plane of the canal he had just cut.
Wait, really?
Yeah, if he cut a horizontal canal, the bird spun horizontally. So this was the very first concrete proof that the inner ear was mechanically linked to spatial orientation.
It's wild to think someone in the 1820s realized this tiny piece of skull architecture is why a bird knows which way is up.
It's incredible.
But observing a spinning pigeon is one thing, right? Figuring out the actual physics of how that bone detects movement, that took decades.
It did. It wasn't until around 1873 that a physicist named Ernst Mach and a physiologist named Alexander Crumb-Brown, working completely independently of one another, by the way, proposed what we now call the fluid inertia model.
The fluid inertia model.
Right. They theorized that the canals in the inner ear functioned as biological accelerometers, heavily relying on the physics of fluids.
Well, let's break down this hardware, because you can't help but marvel at the engineering here. I know from our anatomy sources that deep inside the bony labyrinth, there are two main structures doing the heavy lifting.
Yes.
First, you have the three semicircular canals. But How exactly are those laid out, and what kind of movement are they actually looking for?
So the three canals are arranged roughly perpendicular to each other, representing the X, Y, and Z axes of a three-dimensional space.
Like a 3D gyroscope.
Exactly. And they're designed to detect rotational acceleration. So shaking your head no, nodding yes, or tilting your ear toward your shoulder.
Okay, all rotational stuff.
Right. Each canal is filled with a specialized fluid called endolymph. When you whip your head around, the bony canal moves instantly with your skull. But because of inertia, the fluid inside the canal lags behind for just a split second.
Oh, it's like spinning a cup of coffee. The mug turns, but the coffee inside sort of stays in place and sloshes against the wall of the mug.
That is the perfect analogy. And the biological equivalent of the mug's wall is this gelatinous structure called the cupula.
The cupula.
Right, which sits at the base of each canal on top of a tuft of highly sensitive hair cells. As the fluid lags behind, it physically pushes against that gelatinous cupula, bending the hair cells beneath it.
And that bending is what sends the signal.
Exactly. That microscopic bending triggers a nerve signal that fires to the brain at a rate perfectly proportional to how fast your head is rotating.
Okay, so that perfectly covers spinning, but that's only half the battle. What about gravity? Because what tells me I'm moving forward in a straight line or just standing up? That brings us to the second structure in the inner ear, the otolith organs.
The utricle and the saccule.
Right, specifically those, and these use something called otoconia, which translates to ear dust. Now, tell me I'm misreading this in the sources.
I'm sorry to say you are not misreading it.
Come on.
The sensory hair cells in the utricle and saccule are embedded in a flat, gelatinous membrane, and sitting directly on top of that membrane are thousands of microscopic calcium carbonate crystals.
So you literally have dense microscopic rocks living in your head.
You have rocks in your head, yeah.
That is just incredible. It functions almost like a biological carpenter's level then.
Very much so.
But instead of a little air bubble floating through liquid to tell you if a picture frame is flat, you have these heavy crystals. When you accelerate forward, those heavy rocks lag behind.
Yep, linear acceleration.
Or if you're just standing completely still, gravity is constantly pulling those rocks downward. Right. Continuously bending the hair cells underneath to let your brain know which way is down.
Exactly. The system divides the labor beautifully. The utricle is oriented horizontally to sense linear acceleration, like being pushed back in your seat when a car hits the gas.
Oh.
And the saccule is oriented vertically, so it's perfectly positioned to sense the drop of an elevator.
Between the sloshing fluid in the canals and the shifting rocks in the otolith organs, the inner ear is streaming just a massive amount of data about every conceivable movement.
It's an overwhelming amount of data.
But here is where I get hung up on the mechanics. My inner ear has heavy rocks and fluid, which is great for gathering data. But ears do not have muscles.
No, they don't.
If I trip on a curb, my ear doesn't shoot my arm out to catch my fall. How does the rest of the body actually utilize this ear data in real time?
Well, the vestibular nerve acts as the main data cable. It carries all this information straight into the vestibular nuclei in the brainstem.
Okay, into the brainstem. And then where?
From there, the nervous system fans the signal out to three critical destinations. The first destination is the spinal cord.
The spine?
Yeah, this pathway triggers the vestibulospinal reflex. It is a completely involuntary system that instantly adjusts the muscle tone in your limbs and your core.
So when you trip on that curb, this reflex fires your leg muscles to catch you before your conscious brain even registers that you stumbled.
Exactly. It completely bypasses conscious thought.
So it's totally automatic. Where does the second signal go?
The second signal goes to the cerebellum.
Okay.
The cerebellum is the brain's massive processing center for fine-tuning and calibrating motor output, mostly based on repetition and past experience.
So if there's a problem there, what happens?
Well, when a person experiences a stumbling feeling or uncoordinated movement or chronic imbalance, what clinicians call ataxia, it is often an issue with the cerebellum failing to calibrate the signals rather than a problem with the inner ear hardware itself.
Interesting. Which leaves the third destination, and this one absolutely blew my mind when I read about it.
The oculomotor nuclei.
Yes. This creates the vestibulo-ocular reflex, or the VOR. It automatically counter-rotates your eyes to keep your vision stabilized while your head is in motion.
Right.
And, for you listening to this right now, you can actually test this on yourself. Focus your eyes on an object in front of you, a doorknob, a computer screen, anything. Keep staring at it, and now shake your head side to side pretty quickly.
Notice how the object stays perfectly sharp and clear.
Yeah, it's wild.
Your eyes are moving in the exact opposite direction of your head rotation at perfectly matched speeds without a single conscious thought.
It is a literal biological Steadicam built into the skull. But considering how sprawling this whole network is, integrating the spinal cord reflexes, the cerebellum, the eye muscles, it really makes me wonder about our basic definitions.
How so?
Well, we always talk about the five senses, right?
Yeah.
Given this massive complexity, should we officially classify balance as the sixth sense?
You'd think so, but physiologists generally push back heavily on that classification.
Really?
Because it oversimplifies how the brain processes spatial orientation. I mean, vision and hearing have discrete, dedicated regions in the cerebral cortex. Balance does not.
Oh, it doesn't have its own spot.
No, vestibular information is processed in a widely distributed network across the brain, including areas dedicated to mapping your body in space. And more importantly, the inner ear's data is deeply intermingled with visual processing and proprioception.
And proprioception is, just to clarify, your body's mechanical awareness of muscle stretch and joint position, right?
Exactly. It's how you know where your arm is even with your eyes closed.
So we can't call balance a standalone sense because it's completely codependent on these other systems.
Right.
It's almost more like a backstage manager. You have absolutely no idea it's doing anything until someone misses a cue, and then the whole production just falls apart.
That's spot on. And when a system relies so heavily on integrating diverse data streams and physical parts like microscopic rocks and fluid, it is highly vulnerable to mechanical failures.
And when those failures happen, the resulting sensation is profoundly disorienting.
Oh, absolutely.
Let's talk about those physical glitches, starting with benign paroxysmal positional vertigo, or BPPV, because this goes right back to those calcium carbonate crystals we just talked about, the ear dust.
It does. Occasionally, physical trauma, illness, or even just aging can cause those crystals to become completely dislodged from the utricle.
Oh, so they just pop loose.
Yeah, they drift away from their home base and physically fall into one of the semicircular canals, usually the posterior canal.
Yeah.
Now think about the mechanical error here. You now have heavy, dense crystals sitting in a fluid-filled tube that is strictly designed only to detect fluid rotation.
So every time you tilt your head, like looking up to grab a box off a high shelf, or just rolling over in bed, those rogue rocks violently slosh through the canal fluid.
Exactly. And that physical sloshing triggers a massive, completely false nerve signal to the brain, reporting that you are spinning head over heels.
Even though you only moved your head a few inches.
Right. The vertigo usually lasts for less than a minute, but the rotational hallucination is incredibly intense.
What I found fascinating about BPPV is the treatment. Since it's a mechanical hardware problem, the fix is purely mechanical.
Yes, the Epley maneuver.
Right. Developed by John Epley in 1980. There are no drugs involved. It's not physical therapy to somehow strengthen the ear. Honestly, it reminds me of those little wooden maze puzzles you play with as a kid, where you have to physically tilt the board around to roll a tiny metal ball back into the hole in the center.
The Epley maneuver applies that exact logic to the human skull. A clinician physically guides your head through a very specific sequence of precise angles, utilizing gravity to manually roll those rogue crystals out of the canal and back into the utricle where they belong.
It's incredibly satisfying that you can just, roll the rocks back into place.
Yeah, it is. And it's a structural repositioning that resolves symptoms for the vast majority of patients in a single office visit.
But physical debris isn't the only way to glitch the hardware, is it? We also have to talk about temperature hacking. Walk me through the caloric reflex test, because this part completely broke my brain.
Right, the caloric test. So in the early 1900s, an ontologist in Vienna named Robert Barany discovered a diagnostic technique that is actually still used today.
Okay.
He found that if you irrigate a patient's ear canal with warm or cold water, it induces a temperature-driven convection current in the fluid of the semicircular canal.
Wait, stop right there. How does putting warm water in my outer ear make my eyes involuntarily dart back and forth? What is the actual mechanism connecting water temperature to my eye muscles?
It basically comes down to fluid dynamics. Warm water heats up the bone of the inner ear, which then warms the endolymph fluid inside.
Okay, the fluid gets warm.
Right, and warm fluid becomes less dense and rises. Cold water makes the fluid denser, causing it to sink.
Oh, wow.
So by simply changing the temperature in the ear canal, you force the fluid in the semicircular canal to physically move on its own without the head moving at all.
So the brain feels that moving fluid, assumes the head must be spinning, and fires off that VOR-I reflex to compensate for a spin that isn't actually happening.
Exactly. The brain misinterprets the convection current as a massive rotational acceleration. So the patient, lying perfectly still on an exam table, suddenly experiences involuntary rhythmic eye movements called nystagmus and often profound nausea.
And medical students still memorize this reaction today with the mnemonic COWS, right? Cold opposite, warm as iron. Same, just remember which way the eyes will rapidly beat based entirely on the water temperature.
They do.
It's amazing that Barani figured this out.
It really is. Barani's discovery revolutionized our ability to diagnose vestibular function, earning him the 1914 Nobel Prize in Physiology or Medicine.
And the historical footnote to this is wild. Barani was serving as a civilian surgeon in the Austrian army during World War I and was captured by the Russian army.
Yeah.
He received the news that he won the Nobel Prize while sitting in a prisoner of war camp in Russia. He couldn't even deliver his lecture until he was released in 1916.
Winning a Nobel Prize in a POW camp for putting water in people's ears is a legendary piece of science history.
Truly. But taking this out of the doctor's office, what happens when we take this delicate gravity-dependent system and shoot it into orbit? Space adaptation syndrome must be an absolute nightmare for the brain's predictive models.
Oh, it destroys the brain's baseline data. I mean, without the constant downward pull of Earth's gravity, those otolith organs relying on heavy crystals, they become utterly useless.
There's no up or down.
Right. They suddenly start sending random, chaotic signals or no consistent gravitational signal at all. The brain's carefully calibrated integration of vision, vestibular data, and proprioception just shatters.
So the brain has to adapt by aggressively rewriting its software. It realizes the ear is sending garbage data, so it starts heavily prioritizing vision.
Exactly. Neuroplasticity at work.
But while it's writing that patch, for the first few days in space, astronauts experience severe nausea, disorientation, and vomiting.
Yes. But the human nervous system is remarkably plastic, so it usually adapts to 0G within about 3 days.
Okay, so they get their space legs.
Right. However, the exact same crisis occurs when they return to Earth.
Oh, right.
Their neural model has spent months adapted to weightlessness. When they land, the sudden return of gravity overloads the system. They literally have to relearn that gravity exists, often struggling to stand upright, walk in a straight line, or turn corners without falling over for several days after returning.
That astronaut scenario actually solves one of the biggest mysteries of everyday life, I think. Because sometimes feeling dizzy or sick doesn't mean your hardware is broken at all.
No, not necessarily.
It means your brain is working exactly as evolution designed it, but it's processing the wrong environment.
Exactly. And this is the foundation of the sensory conflict theory of motion sickness, proposed by psychologists James Reason and Joseph Brand in 1975.
Sensory conflict theory.
Right. Their model posits that motion sickness is fundamentally a symptom of mismatched data streams.
So if I'm reading a book in the back of a moving car, my inner ear feels the physical acceleration and the sharp turns. It's screaming, "We are moving rapidly."
Yep.
But my eyes are locked onto a stationary page reporting back, absolutely nothing is moving.
So the brain is presented with a profound contradiction. From an evolutionary standpoint, before cars or boats existed, there was really only one common scenario in nature where a primate's sensory systems would suddenly start reporting wildly different realities.
Which is?
Neurotoxin poisoning.
Wow.
Ingesting toxic plants causes severe neurological confusion that mimics this exact sensory mismatch. So the brain concludes, I must have eaten poison, and it triggers nausea and vomiting as a defensive reflex to purge the stomach.
That reframes motion sickness entirely, so even cyber sickness, right?
Yeah.
When you put on a VR headset and visually fly through a canyon while your body sits still on a couch,
An exact mechanism.
your brain isn't weak or defective. It's aggressively trying to save you from a hallucinated poisoning.
It is a completely healthy universal defense mechanism. But this brings up a broader issue in how we talk about these sensations, particularly in clinical medicine.
Like when people just say, I feel dizzy.
Right. That vague term dizziness is a significant hurdle. Patients use it as a catch-all, but diagnosing the root cause requires separating it into distinct categories.
So what are the categories?
Well, true vertigo is that false sensation of spinning, which points directly to the inner ear.
Right.
But presyncope is a feeling of lightheadedness or faintness, which usually points to a cardiovascular issue, like reduced blood flow to the brain. And then disequilibrium is a feeling of unsteadiness in the legs, which often points to pneumological or proprioceptive loss.
And that distinction is crucial when we look at something like elderly falls, which is a massive public health issue. We tend to assume if someone is losing their balance, their inner ear must be failing. But it goes back to that three-legged stool we talked about earlier. Vision, vestibular, and proprioception.
Exactly. An elderly patient might have a perfectly pristine functioning inner ear, but if they have declining vision from cataracts and they suffer from diabetic neuropathy, which deadens the nerve endings and proprioceptive feeling in their feet, they have lost 2 of their 3 critical sensory inputs.
The stool falls over.
Right. The overall integrative system cannot keep the drone hovering with only one functioning sensor, leading to catastrophic falls.
So if a lack of sensory input causes dangerous falls, and misinterpreting temporary input causes motion sickness, what happens when the brain gets a constant, prolonged input and overadapts?
You're thinking of mal de débarquement syndrome.
Yes, the cruise ship thing.
Right. This condition illustrates the power and the peril of the brain's predictive modeling. When you go on a week-long ocean cruise, your brain spends days experiencing the continuous rhythmic rocking of the ship. To keep you balanced, neuroplasticity kicks in. The brain essentially writes a software patch, updating its internal model to anticipate the continuous movement of the ocean waves.
So when you finally step back onto solid land, your brain expects the ground to move, and it preemptively fires muscle corrections for waves that aren't even there.
For most people, the brain recalibrates to solid ground within a few hours. But in mal de débarquement syndrome, the vestibular system essentially fails to uninstall that software patch.
Oh, that sounds awful.
Patients continue to feel a persistent, debilitating, rocking or swaying sensation on perfectly solid ground for weeks, months, or sometimes years. It disproportionately affects women in their 40s and 50s, and neurology is still investigating exactly why the predictive model gets permanently stuck in this loop.
It is genuinely unsettling that a relaxing vacation can permanently rewrite your brain's physics engine.
It really is.
But motion sickness and cruise ships are relatively low stakes. What happens when you completely blindfold the visual system in a high-speed, three-dimensional environment where physics are pushed to the absolute limit?
That introduces the phenomenon of spatial disorientation in aviation. And that is where a sensory mismatch becomes a literal matter of life or death. Remember that the vestibular system cannot reliably distinguish between a change in orientation and a continuous acceleration without external visual cues.
Let's ground this in a physical feeling for everyone listening.
Right.
If I sit in a spinning office chair, close my eyes, and you spin me really fast, the fluid in my ear pushes on the cupula, and I feel the spin.
Correct.
But if you keep me spinning at the exact same speed for 30 seconds, the fluid eventually catches up to the movement of the bony canal. The cupula straightens out. I will literally feel like I have stopped moving, even though I'm still spinning rapidly.
Yes.
And when you finally stop the chair, the fluid keeps moving due to inertia, and I suddenly feel like I'm spinning in the opposite direction.
That exact physics principle creates what pilots call the graveyard spiral.
The graveyard spiral.
Right. If a pilot is flying at night or in heavy clouds with no visible horizon, they lose their primary sensory input. If the aircraft enters a slow, sustained banking turn, the fluid in the pilot's inner ear eventually catches up to the rotation.
Just like the chair.
Just like the chair. So to the pilot's brain, it feels like they are flying perfectly straight and level, even though the plane is banking sharply toward the ground.
The inner ear is actively lying to the brain. And if the pilot realizes they are losing altitude and pulls back on the yoke, they aren't pulling the nose up. They're just tightening the spiral toward the ground.
Exactly.
This specific sensory illusion was cited as the probable cause in the devastating July 1999 crash that killed John F. Kennedy Jr.
Yes, it was.
He was flying over the ocean in hazy, moonless conditions, completely stripping away his visual horizon.
The JFK Jr. tragedy is a sobering illustration of how an unchecked vestibular illusion can overpower conscious rational thought. When visual confirmation is removed, the internal model completely detaches from reality. Pilots have to be rigorously trained to ignore their own bodily sensations and implicitly trust their artificial flight instruments.
Which goes entirely against millions of years of human evolution.
Completely against it.
It really highlights why dissecting this anatomy isn't just, medical trivia. Understanding these hidden mechanics dictates pilot training curricula to save lives. It drives the engineering of virtual reality headsets, managing frame rates to prevent hallucinated poisonings,
Right.
and it guides public health strategies to prevent elderly falls by addressing the entire sensory network, not just the ear.
The balance system is the unseen scaffolding of human experience. It dictates how we interact with the physical world on every conceivable level.
So, to summarize our deep dive today, balance is not a passive rock in a bowl. It is an active, predictive drone computation. It relies on a three-part integration of your eyes, your proprioceptive muscles, and an inner ear that uses sloshing fluid to detect spinning, and microscopic calcium rocks to detect gravity.
Nicely summarized.
And when those signals clash, your brain's attempts to protect you can cause everything from motion sickness to fatal spatial disorientation. We have covered incredible ground today. What is one final lingering thought you want to leave everyone with?
Well, consider this. Every single time you feel perfectly still, sitting in a chair, lying in bed, or standing on a sidewalk, you are not actually experiencing a lack of movement.
What do you mean?
You are experiencing an active, highly constructed neurological illusion of stillness.
An illusion of stillness.
Yes, your brain is burning immense energy right this second, constantly cross-referencing data to convince you that you're stationary. And that entire illusion is heavily dependent on microscopic ear dust, acting as your personal anchor to a spinning planet.
I am never going to experience sitting still the same way again. It's a biological miracle. We aren't all just falling over constantly. Thank you for joining us on this deep dive. Go out there and appreciate your ear dust today. Catch you next time.